All right, welcome to the deep dive. The show that takes, those like really complex ideas, those fascinating corners of knowledge, and we try to unpack them in a way that makes them surprisingly clear. And today we're going to be diving into something that honestly sounds a bit like science fiction, but it's really the very foundation of how the universe operates at the smallest scales. It's quantum mechanics. I'm sure you've heard of some of these almost unbelievable ideas of particles acting like they're waves, things being in multiple states at the same time. And you're probably like, what's really going on here? Well, that's what we're here to explore today. Consider this deep dive our expedition into this fascinating and fundamentally strange world. We're going to uncover its core concepts, and we'll touch on the mathematical language that describes it.
Yeah, absolutely. So today we're aiming to extract the really essential insights of quantum mechanics and mathematical thinking that sort of underpins the whole thing. We're going to be drawing from Physics Liber texts, Innovation News Network, and those really helpful Wikipedia entries, on both quantum mechanics and the mathematical formulation of it. And really our aim here is to help you guys develop a solid grasp of these core principles. Really shoot for those aha moments of clarity, all without getting too bogged down in excessive technical detail. So get ready to have your everyday intuition challenged a little bit as we venture into the quantum landscape.
So let's start with something pretty fundamental. Quantum mechanics has this sort of central rule, like an operating system for this quantum world, that tells us how these quantum systems evolve over time. It's known as the Schrödinger equation, and it's kind of like the quantum counterpart to those classical laws of motion, Newton's laws of motion, that you probably learned back in high school physics. So this equation describes how the quantum state of a system changes. It looks like this. Partial. Now, I know that might seem a little bit intimidating at first, but let's break it down and see if we can understand the key ideas here.
One of the most interesting things here is this concept of the Hamiltonian operator, which is represented by that symbol. Think of this as the energy manager for the entire quantum system. It embodies the total energy of the system, combining both the energy associated with motion, kinetic energy, and any stored energy, potential energy. And a really crucial aspect of the Schrödinger equation in this Hamiltonian is what we call linearity. What this basically means is that if you have two possible states that a quantum system could be in, it can also simultaneously exist in a combination of those two states. It's kind of like saying, okay, imagine a light switch. In the classical world, it's either on or it's off, right? But in the quantum world, it can be thought of as being both on and off at the same time until we actually look at it.
Whoa, that's a pretty wild concept. Now, if we take a simple case, just to keep things a bit manageable, let's say we have a single particle that's moving along a straight line. The Hamiltonian operator often takes a form like this, frac partial by 2 plus Vx. You can see there are two main parts here. The first part, that first term, is all about the particle's kinetic energy, how much it's moving. The second part represents its potential energy, which might come from, say, an external force or field that's acting on it.
And if we step back a little bit and look at the bigger picture, the fact that the Schrödinger equation is what we call first order in time has a pretty profound implication. It basically tells us that if you know the precise quantum state of a system at any one moment, you can use this equation to predict its state at any other point in time, whether it's in the future or the past. This ability to track how the system evolves over time is what physicists call time evolution in the quantum realm. What's more is that this equation ensures that the total probability of finding that particle somewhere in space stays constant over time. So if we know for certain, a 100% chance, that the particle is somewhere at the beginning, that certainty doesn't just disappear. It's guaranteed to still be true at any later time. It's just that the specific location where we're most likely to find it might shift.
So we have this rule, the Schrödinger equation, describing how things change, but what is it that's actually changing? That's where this thing called the wave function, represented by, comes in, right? But this isn't like a physical wave like sound waves or water waves, is it?
No, you're right. The wave function is all about describing the quantum state of the system. It's not a directly observable wave in the traditional sense, but it's incredibly important because it's directly tied to the probability of finding a particle at a specific point in space, which we call x, at a particular moment in time. Think of it this way. The wave function itself isn't the particle, but it's like this blueprint that holds all the information about where that particle is most likely to be. More precisely, the probability of finding the particle in a certain region of space is connected to the square of the magnitude of the wave function in that region, which we write as In a more abstract mathematical sense, we think of this wave function as a vector in a really big multidimensional space called a Hilbert space. This space is what allows for those combinations, those superpositions that we talked about earlier.
So the wave function gives us probabilities, not certainties, which is a huge shift from how we think about things in classical physics, where we expect definite positions and velocities. You mentioned earlier that E alpha actually represent the same physical situation. What's the significance of that extra factor?
That term is what we call a global phase factor. What's fascinating is that this overall phase doesn't actually impact anything we can directly measure. It's like taking a photograph and adjusting the overall brightness of the whole picture. You're not changing the objects in the photo or how they're arranged, are you? The information content is the same. It's the same with the wave function. It's the relative differences in phase between different parts of the wave function that actually determine the observable characteristics of the quantum system.
So we talk about the Schrödinger equation describing how things change, but we also sometimes hear about systems being in a stationary state. What does that mean?
This is where something called the time-independent Schrödinger equation becomes really useful. Using a mathematical trick, a technique to separate out the time dependence from the Schrödinger equation, we sometimes get an equation that depends only on the particle's position. You'll notice that the Hamiltonian is now operating only on a function of position, and the result is just that same function multiplied by a constant for epsilon.
And that constant for epsilon represents the total energy of the system when it's in that state, right?
Yeah.
This seems like a special kind of equation where applying that Hamiltonian operator just scales the original function.
That's exactly right. For epsilon represents the energy eigenvalue, and that ux is the corresponding eigenfunction. If we take these eigenfunctions and we multiply them by a simple time-dependent factor, we get what we call stationary states. The key feature of these states is that the probability of finding the particle at a specific position, represented by u epsilon, doesn't actually change over time. The underlying wave function itself does change with time, but the probability distribution stays constant. A good analogy here might be a guitar string vibrating in a fixed pattern. The string itself is moving, but the overall shape of the vibration pattern remains the same.
Yeah, that makes sense. So a general quantum state can then be a combination, or a superposition as we've been calling it, of these basic stationary states, each with its own distinct energy.
Exactly. A general solution can be represented as a sum or sometimes an integral of these stationary state solutions, each multiplied by a specific amount, which we label as C, or SUTHO, and its associated time-dependent factor. This idea is really powerful because it lets us understand complicated quantum behavior by breaking it down into these simpler time-independent components. And what's really neat is that these stationary states actually have a connection to Niels Bohr's early model of the atom, where he proposed that electrons orbited the nucleus in specific stable energy levels without losing energy. Now, quantum mechanics gives us the actual mathematical framework to calculate these energy levels and the shapes of those electron orbits, which we now describe using wave functions.
Now, you mentioned eigenvalues earlier. It sounds like this is a pretty important concept. So what exactly do we mean by the energy spectrum?
The energy spectrum is simply the set of all the possible energy eigenvalues, the ver epsilon values, that satisfy the time-independent Schrödinger equation for a specific quantum system. These eigenvalues represent the only allowed energies that the system can have. Think of it like climbing a staircase, where you can only step on specific stairs, not in between them. And here's something interesting. You can sometimes have multiple different eigenfunctions, like that all correspond to the exact same energy eigenvalue. When that happens, we say that energy level is degenerate. It's like having different musical notes that all have the same pitch.
So different wave function shapes can have the same energy. That's pretty wild compared to our everyday experience.
Yeah.
Do these eigenfunctions themselves have any special mathematical properties?
Yes, they actually do. We typically choose eigenfunctions that are orthonormal. Orthogonal essentially means that if you take two different eigenfunctions and you sort of combine them mathematically in a specific way, the result will be zero. This means they are, in a sense, perpendicular to each other in this abstract mathematical space. Normalized, on the other hand, means that if you combine an eigenfunction with itself in that same mathematical way, the result will be 1, which we interpret as a 100% probability of finding the particle somewhere in space. Mathematically, this is expressed as d x d x Whiston, where is the symbol that equals 1 when n and n are the same and 0 when they're different. And for those degenerate eigenfunctions that share the same energy, we can also find a set that are orthonormal, which is expressed as Inkmen x d x delta.
All right, we've talked about the quantum state and this wave function, but how do we actually extract information about physical properties, like the position of a particle or how fast it's moving from this wave function? This is where we need those things called operators, right?
Exactly. In quantum mechanics, any measurable physical quantity, which we call an observable, is represented by a mathematical operator. These operators act on the Hilbert space of the system, transforming wave functions into other wave functions. For example, the operator that represents the position of a particle along the direction is simply the act of multiplying the wave function by x. The momentum operator, on the other hand, is a little more complex. For the momentum along the direction, it's represented by Eiger partial, which involves taking a derivative of the wave function. And as we talked about earlier, energy is represented by that Hamiltonian operator.
Okay, so these operators act on wave functions, but how do we actually get a specific number, a measurement, like the momentum of a particle in a particular quantum state?
To get a measurable number, we use the concept of the expectation value. The expectation value of an operator, let's call it in a specific quantum state, gives us the average value we would expect to get if we measured the corresponding physical quantity many times on a whole bunch of identical systems that are all prepared in the same quantum state. In 3 dimensions, it's calculated like this. And a really crucial point here is that for any physical quantity that we can measure, the corresponding operator has to be self-adjoint, which is also called Hermitian.
Self-adjoint, what's the importance of that?
Well, a self-adjoint operator has a specific mathematical property that guarantees that its expectation value will always be a real number. This is really important because any physical measurement we make in the real world always gives us a real number as a result. Mathematically, for an operator to be self-adjoint, it has to satisfy this condition, D3, math B3 for any well-behaved wave functions. Now, this is where things start to get really interesting, even a bit mind-boggling. You mentioned that the order in which we apply these operators can actually matter in quantum mechanics. That's not how things usually work with regular numbers, right? You're absolutely right. This is one of the key differences between quantum mechanics and classical physics. In the quantum world, the order of operations really can make a difference. For example, imagine measuring the position of a particle first, then its momentum. You might get a different result than if you measured the momentum first and then the position. This order dependence, or non-commutativity, is captured mathematically by the commutator of 2 operators, which is defined as hat A, hat AA. If the commutator is 0, the order doesn't matter. But if it's not 0, then the order of those operations actually does matter.
So for the position along the axis and the momentum on that same direction, what's their commutator?
Well, it turns out that the commutator for the position operator and the momentum operator equals, where I is the imaginary unit and is the reduced Planck constant. This seemingly small value has huge consequences. In fact, there's a set of fundamental rules called the canonical commutation relations that essentially govern how different pairs of operators behave. Left L bar, cod delta. What these relations tell us is that if you're measuring positions in different directions, like x and y, the order doesn't matter, and the same goes for measuring momenta in different directions. But if you're dealing with position and momentum along the same direction, like the x position and x momentum, then the order in which you make those measurements absolutely does matter.
And this whole idea of non-commutativity is what leads to one of the most famous principles in all of quantum mechanics, Heisenberg's uncertainty principle, right?
That's exactly right. Heisenberg's uncertainty principle comes directly from the fact that certain pairs of operators, such as position and momentum, don't commute with each other. Now, to measure how spread out the probabilities are for a specific observable, we use the concept of variance. The variance is basically a measure of how much the possible measurement outcomes are scattered around the average or expectation value. It's defined as delta right angle, left angle, Lorentz, the uncertainty principle, specifically when we're talking about position and momentum in one dimension, states that the product of the uncertainties for these 2 quantities, more accurately, the product of their standard deviations, which are the square roots of the variances, must always be greater than or equal to. So in simpler terms, what does this limit actually mean for our ability to know things about a quantum particle? It essentially means there's a hard limit on how precisely we can simultaneously know both the position and the momentum of a quantum particle. If we manage to pin down the position of a particle with really high accuracy, then our knowledge of its momentum, how fast it's moving and in what direction, will become inherently fuzzy. And of course, it works the other way around too. This isn't a problem with our measurement tools or our experimental techniques. It's an inherent property of the quantum world. It's a fundamental limit on what we can know about these particles.
We also touched on this idea earlier that energy levels in quantum systems can be discrete. It's not a smooth, continuous spectrum of energies, but more like steps on a staircase. This is the concept of quantization. Right. Can you give us an example of this? Yeah, quantization is a great way to describe it. It's the idea that certain properties in the quantum world can only take on specific, distinct values. A classic example, and one that physicists use all the time, is the quantum harmonic oscillator. You can think of it as a model for anything that vibrates at the atomic level. The energy levels for a quantum harmonic oscillator are given by this formula. Var epsilon nu plus frac 1, 2 in this equation can only be a whole number, 0, 1, 2, and so on, and omega is the frequency of the oscillation. What this means is that the energy of the oscillator can only be certain multiples of bar omega plus this minimum energy, what we call the 0-point energy, which is frac 1 mega. This staircase nature of the energy levels, this quantization, is a key signature of quantum mechanics.
And then we have this concept of superposition, which keeps coming up over and over again. It seems like a central idea in all these quantum phenomena.
Superposition is definitely a big deal. It describes this incredible ability of a quantum system to exist in a combination of multiple states simultaneously, each with a certain probability associated with it. The wave function basically encodes all these probabilities, and its evolution is governed by that Schrödinger equation we discussed. This concept is maybe one of the hardest to wrap your head around because in our everyday macroscopic world, things are always in one definite state or another. But superposition isn't just a theoretical concept. It's the backbone of some really exciting new technologies, particularly in the field of quantum computing. Quantum computers use quantum bits, or qubits, which can exist in a superposition of 0 and 1 at the same time. This lets them tackle problems that are way too complex for even the most powerful classical computers.
And we can't forget quantum entanglement, which is a term we hear a lot about. Where does that fit into all of this?
Quantum entanglement is one of those things that really makes you question everything you thought you knew about reality. It's this amazing phenomenon where two or more particles get linked together in such a way that their fates are intertwined no matter how far apart they are. If you measure a property of one of the entangled particles, you instantly know the corresponding property of the other particle, even if they're light years away. Einstein famously called this spooky action at a distance. Entanglement is a basic feature of quantum mechanics and is playing a huge role in fields like quantum communication and quantum information processing, potentially opening the door to incredibly secure communication and new forms of computation.
And finally, what happens when we actually make a measurement on a quantum system that's in a superposition of states? This is where the idea of wave function collapse comes in, right?
Yeah, measurement in quantum mechanics is a really tricky topic, and it's something that physicists are still actively researching and debating. In the standard interpretation of quantum mechanics, one way to think about it is that the act of observing, of measuring a property of a quantum system, forces it to choose one of its definite states. The probability of getting a particular outcome is given by the Born rule, which says it's connected to the square of the amplitude of the corresponding part of the wave function just before the measurement. But this idea of a sudden collapse of the wave function, it's something that a lot of physicists find troubling, and there are alternative interpretations, like the many worlds interpretation, which suggests that instead of a collapse, the universe essentially splits into multiple parallel universes, each representing a different possible measurement outcome. In this view, the observer becomes entangled with the system, so they end up experiencing one specific outcome in their branch of the multiverse. But more modern perspectives often put more emphasis on the entanglement between the system being measured, the measuring device itself, and the surrounding environment, which all combine to make it seem as though a collapse has happened. And the mathematical framework that underlies all these concepts relies heavily on this idea of Hilbert spaces, which are basically these really big abstract spaces that can accommodate all the possible quantum states of a system. And the observables, those measurable quantities, are represented by linear operators that act on these Hilbert spaces, and the possible values we can measure, the eigenvalues, are fundamental properties of these operators.
Right, and we briefly mentioned the Schrödinger picture earlier,
Mm-hmm.
where the quantum states are the things that evolve over time. Are there other ways that physicists think about this time evolution?
There are actually other ways to mathematically describe how quantum systems change with time, which are all equivalent in terms of the predictions they make, but offer different perspectives. So in the Schrödinger picture, the states, those wave functions, are what change with time, while the operators representing the physical quantities stay fixed. But in the Heisenberg picture, it's the opposite. The states are considered to be fixed, and it's the operators themselves that change over time according to their own set of equations that involve the Hamiltonian of the system. And there's also a third picture called the Dirac picture, or sometimes the interaction picture, which is kind of a mix of the two. In this picture, both the states and the operators evolve over time, but they change in response to different parts of the system's energy, which is helpful when you're dealing with systems that have a strong free part and a weaker interaction part.
So much to think about. Let's just recap some of the key takeaways. In a nutshell, the quantum world operates based on probabilities, and the central equation that governs everything is the Schrödinger equation. We encountered these really strange and fascinating concepts like superposition and entanglement, which completely challenge how we normally think about reality. And all of this is underpinned by a powerful and elegant mathematical framework built on the ideas of operators, eigenvalues, and Hilbert spaces. And we can't forget Heisenberg's uncertainty principle, which tells us there are inherent limits to what we can simultaneously know about certain pairs of properties of quantum particle.
Exactly. And it's pretty amazing to consider that all these foundational principles, which are so different from our everyday experience, aren't just abstract theories confined to physics textbooks. They form the basis of many technologies that are rapidly transforming our world. Everything from the incredible potential of quantum computers to the development of super precise sensors.
So, dear listener, you've just taken a deep dive with us into this incredible quantum realm where probabilities dance and particles blur. But why stop exploring here? Stick with us on the All Sorts podcast. We have a whole universe of conversations waiting to be had. Like a wave searching for its crest, let your curiosity guide you. Make sure to like, share, and subscribe to All Sorts podcasts on YouTube, where new dimensions of understanding await. Dive into our archive, a vast collection of past deep dives into all sorts of fascinating topics, and join our growing community on X, Instagram, and Threads. Let's entangle our minds in the wonders of the universe, one conversation at a time. And as we continue to learn more about quantum mechanics, what other astonishing realities might we uncover? Perhaps the answers lie in future deep dives right here on the All Sorts podcast. Thank you for listening.